As a general rule, bond strength and bond length are inversely proportional. So the stronger your bond, the shorter that bond is, and the weaker your bond, the longer the bond is. So we can look at single bonds, double bonds, and triple bonds. Single bonds are the weakest bonds, and they happen to be the longest. Triple bonds, on the other hand, are the strongest bonds, and they're also the shortest. So we can look at this numerically using examples with carbon-carbon bonds. We'll look at bond length in angstroms, which is just 10 to the minus 10 meters. And we'll look at bond enthalpy, which is effectively just a measure of bond strength. And we'll use that in kilojoules per mole. So kind of approximate average bond lengths go from carbon-carbon single bonds at 1.54 angstroms to carbon-carbon triple bonds at roughly 1.2 angstroms. And we can see that the bond enthalpies and the bond strengths are going to follow the opposite trend. And we see that the carbon-carbon single bonds are relatively weak at 348 kilojoules per mole, all the way up to carbon-carbon triple bonds, which are very strong at 839 kilojoules per mole. And it's possible to rationalize that when you look at the Lewis diagrams for each of these types of bonds. If we look at a carbon-carbon single bond, we know that each carbon will be contributing one electron. So there'll be 2 electrons between the carbon atoms, and the other electrons from each carbon will be off to one side. But effectively, we're in a situation where carbon's got a nuclear charge of 6, and there are 2 electrons in between the carbons. So there'll be a certain amount of attraction pulling those carbon atoms together, making the bond. In a carbon-carbon double bond, we have a similar situation, but with more electrons in between. And again, we've got a situation where we've got 6 positive charges, the charge in the carbon nuclei, and now we've got 4 electrons in the middle, so it's a larger charge pulling the atoms together. And the same kind of thing is true for a triple bond. You've got 6 positives for the carbon nuclei, and now you've got 6 electrons in the center pulling those atoms closer together. And this is, remember, an electrostatic attraction, so it follows this expression, where the strength of that attraction is going to be related to the magnitudes of the charges. So one of the charges would be the positive charge, and one of the charges would be the negative charge. So as you add more negative charges in between the nuclei, the strength of that attraction gets bigger.